Hold a metal rod to a roaring flame. Within seconds, your bare hand will drop it. Heat travels down the solid metal, transferring energy from the fire directly to your skin. This is conduction. It is the physical flow of thermal energy between adjacent parts of a body due to a difference in temperature, and it happens entirely without the material itself visibly moving. While gases and liquids are relatively poor at conducting heat, solid materials excel at it. Their tightly packed molecular structures allow vibrating atoms to quickly pass kinetic energy down the line. But simply knowing that heat moves isn't enough to build safe technology. To design anything from a cooking pot to a spacecraft, engineers have to calculate exactly how fast that thermal energy is traveling. Mastering the mathematics of conduction allows us to accurately predict that speed. Getting those calculations right means building an efficient machine. Getting them wrong means a catastrophic thermal failure. To calculate this speed, physicists isolate the variables. Imagine a uniform metallic bar with a specific length and cross-sectional area. We connect it to a hot source on the left, let's call it TC, and a cold destination on the right, TD. We fully insulate the sides so no heat escapes into the surrounding air. When the heat first enters the bar, the temperature inside fluctuates wildly. But over time, the interior temperature stabilizes into a perfectly smooth, unchanging gradient, stepping down uniformly from the hot end to the cold end. This specific condition is called the steady state. It is the moment when the temperature decreases evenly with distance, and the chaotic initial warm-up phase is completely over. Once we reach the steady state, thermal energy flows through the bar at a constant rate. We measure this constant flow using a metric called heat current, represented by the letter H. By waiting for the steady state, physicists take an unpredictable burst of thermal energy and turn it into a highly predictable, mathematically solvable current. If you crank up the heat at the source and lower it at the destination, the heat current accelerates. The rate of flow is directly proportional to that temperature difference between the two ends. Next, if you widen the cross-sectional area of the solid, labeled A, you provide more physical space for the thermal energy to travel through. This also increases the total heat current. Conversely, stretching the solid makes the energy travel a greater distance. This longer length L acts as a bottleneck, actively slowing down the overall rate of heat flow. Putting these physical dimensions together, we find that heat current is directly proportional to the cross-sectional area multiplied by the temperature difference and inversely proportional to the length. This mathematical blueprint tells us exactly how dimensions and temperature interact, but the equation is missing something crucial. It ignores what the bar is actually made of. To turn this proportional relationship into a strict mathematical law, we introduce a constant of proportionality, K. This is known as thermal conductivity. Thermal conductivity is the unique thermal fingerprint of every substance. It dictates a material's innate atomic ability to conduct heat. We measure this constant in specific SI units, joules per second per meter per Kelvin, which is more commonly expressed as watts per meter per Kelvin. This chart shows just how extreme the variance in thermal conductivity can be across different materials. Metals like silver and copper have massive K values, near 400. In sharp contrast, insulators like glass, wool, and air sit near 0, creating a physical barrier to heat. A material's K value determines its physical role in engineering, functioning as a rapid superhighway for thermal energy or an impenetrable shield against it. This is why premium cooking pots feature heavy copper bases. The extremely high thermal conductivity of copper forces heat from a single burner to instantly distribute across the entire bottom, ensuring your food cooks evenly. On the opposite end of the spectrum, architects pack roofs with thick foam and concrete. These materials contain tiny pockets of trapped air, utilizing air's ultra-low thermal conductivity to block oppressive summer heat from entering a building. But the stakes get much higher. This is the shipping port power station reactor vessel, one of the most extreme thermal environments on Earth. Inside a nuclear core, the fission process generates an overwhelming amount of heat. To prevent the core from overheating and melting down, engineers design elaborate heat transfer systems. They rely entirely on precise calculations using high conductivity materials to pull that enormous energy safely away. Understanding the exact mathematics of conduction allows us to build everything from a reliable skillet to a secure nuclear reactor. It is the steady, calculable heartbeat that governs human survival and advanced engineering.